Hello students, Dr. Daniel Andrews here. So today we've got our first in a series of organic chemistry lectures. So there'll be 4 of these coming up, and it builds on what we did in the first part of the course with chemistry, and then also bridges to the next part where we're looking at macromolecules like proteins, carbohydrates, lipids, etc. So it's a really important part of the course to get this overall understanding of what we're doing. So we're going to start looking more at the structures of compounds and trying to work out how they behave based on those structures. So as always, we've got our key concepts for the session that you can see here on the slide. So we've got our session 7 key concepts, and these come from the conceptual questions at the end of your tutorial. So you can see some of the important things we're going to be looking at today. Organic compounds, that's going to be one of our major focus. So an organic compound is just something that contains carbon. So we're going to look at some of the differences between organic and inorganic compounds. So the main difference being the presence or absence of carbon. So if it has carbon in its structure, makes it organic. If it doesn't, then it's inorganic. So we're going to also have a look at what causes compounds to form. So as we know, individual atoms come together to form compounds and molecules. So we're going to look at why atoms actually want to come together to form these compounds. And we'll also look in depth at the bonding of the carbon atom, which is quite unique. We'll then talk a bit more about something called a hydrocarbon, which is a compound made up of just hydrogen and carbon atoms. And these can be in either saturated or unsaturated forms. They can also adopt straight chain structures where all the carbons are lined up in a straight line, or they can actually form a ring-like structure. So some of you might have seen structures of like glucose or other sugars represented as rings, which they often are. We'll also introduce the idea of a functional group. So a functional group is a site within a compound that is particularly reactive. So particularly in the 3 sessions coming up, we're going to be focusing on what these functional groups are and what they do. The most well-known one of these is the alcohol functional group, which we summarize as ROH. R just being a placeholder and the OH representing an oxygen and hydrogen. We'll also have a look at the number of functional groups that can be in a compound. There's no limit, really. It just depends on what the compound is. So you could have 1 or even up to 100 functional groups, depending on if it's a really large compound. And the last thing we'll have a look at is stereoisomers, which are pairs of compounds that have a lot of similar properties, but they are different in one particular way. So we've got our lecture here divided into roughly 3 parts. So we're just going to be firstly looking at how compounds are actually formed and some of the distinctions here between what makes something organic versus inorganic. And we're going to then move on to actually being able to draw these structures. So how do we draw a correct structure of a particular compound and the different representations that we can do there. So as we'll see later on in the session, you can have different representations for the same compound. For example, C3H8 can be represented in a form where we completely draw out every single atom with the carbons connected and then the hydrogens as well. So I'll show you some ways to work out where the atoms are actually going to be placed within these compounds. But basically, it comes down to how many covalent bonds each atom has to form. And as we've seen from earlier lectures, carbon always needs to form 4 covalent bonds and hydrogen 1 to allow the outer shell or valence shell to be full. And the last part of the session is focusing on the functional groups and other characteristics of organic compounds. So part 1, let's have a look at the difference between organic and inorganic compounds. So our definition for organic compounds is one that contains a carbon atom. So that is the key characteristic of an organic compound, something that has carbon in it. So if you ever see a compound with a carbon atom, then you automatically know it has to be an organic compound. So you can see that in the definition here. Carbon atoms have to be present. So it can be one or it can be more than that. So why these organic compounds are so important is because we rely on them for life, essentially. So things like carbohydrates, lipids, proteins, fats, and our nucleic acids, our DNA and RNA, are all organic compounds. You might have heard the term carbon-based life form, and we are a carbon-based life form because all of these macromolecules that are essential to life, that they are all containing carbon atoms. So here we can see a structure of a hydrocarbon, which is an organic compound that contains just carbon and hydrogen. So it's actually the structure that I drew on the slide back here. So we've got the 3 carbons and the associated hydrogens. So you can see a line between many of these atoms here. So as we can see in this representation here, it's telling us that each line actually represents a covalent bond. So you can see between these 2 carbons we've got a covalent bond, just like there's a covalent bond between this carbon and this hydrogen. So every time we've got a line there, that's a covalent bond, and that's representing a sharing of 2 electrons between those atoms involved. And down the bottom here we've just got a little representation of our DNA, which remember is another one of our organic compounds. So to summarize, what is an organic compound? It's something that contains a carbon atom. So the majority of the compounds that we see in this course are actually organic compounds. So here we can see some of the representations of the groups that I was just talking to you about. So we've got our carbohydrate. Here is a glucose structure. It's actually a ring structure of glucose. So each point of the ring here, where there's no atom shown, is actually a carbon. And we've actually got some functional groups in here as well, an alcohol and an ether. We'll introduce these in later sessions. The main dietary lipid we have in our fats and oils that we consume is called triacylglycerol, and it's got this characteristic structure where we've got a long chain of hydrocarbons at the end here, represented as a zigzag, and then we've got some of the connecting functional groups in the center here. Our DNA and RNA has quite a complex structure. As you can see here in the pink, we've actually got 3 separate parts, which we'll have a look in a little bit more detail in a later lecture. But again, lots of different functional groups in there. And one of the most important molecules we have in our body is our proteins. So these are the little worker bees. There's a protein to help out pretty much any process you can think of that's going on in the human body. So one of the most famous is that hemoglobin that carries the oxygen in the red blood cells to allow oxygen to get to our tissues and cells. So proteins are actually made up of these individual units called amino acids. So again, we can see that there's these 2 functional groups here, an amine and a carboxylic acid. So what's common about all 4 of these different classes of macromolecule that I've got in this slide here? Well, they all contain carbon atoms. So whether you have carbohydrate or protein, it's still an organic compound. So remember, these are the compounds that make life possible, and they all contain carbon. So we wouldn't be getting too far without carbon, as you can see from this slide. But not all compounds contain carbon, do they? So that's where we have our inorganic compounds. And these are the compounds that do not contain carbon atoms. We've seen some of these already in the course. For example, water, H2O, no carbon there. NaCl, one of our ionic compounds, also known as table salt. Again, no carbon atoms. But again, we can represent these structures just in the same way. So here we have a covalent compound, which is water. So we've got the oxygen atom connected to two hydrogens, each via a line representing the covalent bond. So we can see here a droplet of water pooling on a leaf. So it's got this bead-like structure because the individual water molecules are actually more attracted to each other than they are to the leaf. So what's the main difference between an organic and an inorganic compound then, based on what I've shown you so far? So all you really have to look for is whether the compound contains a carbon atom. If it contains a carbon atom, we can call it an organic compound. For example, those carbohydrates and proteins I showed you, they were organic. Whereas compounds that we see on this slide with no carbon atoms, like water and table salt, these are inorganic compounds. So a little bit more about water here. So what makes water so vital? Well, you've probably heard that around half the human body is actually made up of water. So we're very reliant on it. And one thing that we need water to be able to do is to actually move components within the body. So as well as our body being made up of mostly water, a large part of the cells actually have water in them as well. So this water actually allows things to be transferred in and out of cells as well as the water moves. So vital that we're not dehydrated and able to take in enough water to sustain all these processes. So as you can see in this representation down the bottom here, we've got water being able to be represented in these three states. So it can either be in the solid form of ice. If we melt it, then it becomes a liquid. If we add even more heat energy to it, it then becomes steam. So obviously in the body, it's going to be in the form of a liquid. Alright, so here we have a comparison of what makes something organic versus an inorganic compound. So here we can see the distinction. The organic contains one or more carbon atoms, whereas the inorganic don't have any carbon atoms at all. So most often the organic compounds are going to be covalent compounds. So that means that the atoms within that compound are connecting together via electron sharing. So you can see each of these lines in our hydrocarbon structure is a covalent bond. So we would call this then a covalent compound. So if we compare this to inorganic, some of the inorganic compounds will be covalent and some will be ionic, depending on which atoms are involved. So for H2O, that's a covalent compound because it contains two nonmetal atoms that are forming covalent bonds together. That's the oxygen and the hydrogen. So if we compare this to the sodium chloride down the bottom here, NaCl, you can see that they've actually become ions to form this interaction where they're attracted together. So we've got the positively charged sodium and the negatively charged chlorine. So this makes it an ionic compound. So in general, we can say that organic compounds are going to be covalent, whereas inorganic compounds may either be covalent or ionic. But usually, or more often than not, they are ionic, but there can be some covalent ones as well. But remember, the easiest way to distinguish between organic and inorganic compounds is just to look at whether they contain carbon atoms. Have carbon atoms, organic. Do not contain carbon atoms, inorganic. So we've talked a little bit already about hydrocarbon compounds. These are the most basic forms of a organic compound. So these are organic compounds that contain only carbon and hydrogen atoms. So you can see in the structures down the bottom, each atom present is either a carbon or a hydrogen. So these types of compounds exist naturally, and they can also be created in the laboratory. So with our hydrocarbons, they can either adopt a straight chain form. So you notice that all the carbons in this left-hand representation are in a straight line, whereas on the right-hand side here, they're actually forming a ring structure. So what is one of the main differences between these two representations, whether it be a straight chain or in a ring structure? Look at the ends of each compound. So if we look at the straight chain here, there's two well-defined ends. What about on the right-hand side here? Where's the end? Well, because it's a ring structure, there's no end. So that's one of the major differences between a straight chain or a ring structure for a hydrocarbon. If it's in a straight chain, it has well-defined ends, whereas if it's in a ring structure, there are no ends because it's a ring. So again, just like all our other representations, we saw that the line represents a covalent bond where two electrons are being shared. In the right-hand representation here, we have a slightly more simplified version of the structure. So when we see a CH2, it actually is representing a carbon bonding to two hydrogens like this, but instead of writing that out every time, we can just summarize that as CH2. So that's another difference between these two structures, because all of the carbons in the ring structure are CH2s, whereas in the straight chain structure, some of those carbons are actually bonded to three hydrogens, and some, or one, is bonded to two hydrogens. So another distinction that we'll look into in a little bit more detail later on. So one of the most important things to take away from this session is the knowledge as to why atoms actually come together to form compounds. So we have touched on this in earlier sessions, but let's go into it in a little bit more detail now. So the key reason why atoms want to form compounds is because it can actually make them more stable. Atoms will do whatever they can to adopt a more stable state. And once the atoms are in an arrangement in a compound, they're in a more stable state. So what is it about being in a compound that's going to make the atoms more stable? Well, it comes down to how full the electron shell is. So for an atom to be stable, its valence electron shell must be full. So essentially what happens when atoms come together to form a compound is it allows them to do these electron sharing relationships, covalent bond forming, to actually get enough electrons in their outer shell for it to be full, to satisfy the octet rule by having 8 electrons in that outer shell. So if you compare this to an individual atom that's not in a compound, those ones aren't going to have the full valence electron shells. So this makes them less stable. The exception to this is the noble gases, which naturally have 8 electrons in their valence shell because they're in group 8 in the periodic table. But all of the other atoms on the periodic table need to form some sort of bonding relationship to allow the full valence electron shell to be adopted. So here we can see a representation of water where we've got an oxygen bonded to 2 hydrogen atoms via covalent bonds. So by adopting this arrangement, the hydrogen, oxygen and the other hydrogen are all stable because they have full valence electron shells. So what is it that was able to give these atoms full valence electron shells? Well, it was actually the electron sharing relationships between the atoms involved. So they were able to get the number of electrons they needed to fill their valence shells. So if we compare that to each of these individual atoms on their own, not bonded together, that means the atoms do not have full valence electron shells, which makes them less stable. So we can say that the individual atoms are unstable compared to the stable atoms that are a part of the water molecule. So this is the inherent reason as to why compounds are formed. Atoms come together to form the bonds that make them more stable to get the full valence electron shell. So this is what's driving all atoms to connect to each other essentially. So if this wasn't true, then the atoms would all just be pinging around doing their own thing and nothing would actually exist, because everything you see around you is just a collection of atoms that have come together in a specific arrangement. Very complex arrangements, but arrangements nonetheless. So we need the ability of these atoms to want to stick together to fill their valence shells to actually create larger compounds. So a little bit of more detail about the valence shell and how and why this needs to be filled. So as we saw in an earlier session, it's actually the atom's electrons that are responsible for forming bonds with other atoms. So if you want to go into a little bit more detail, we need to actually pair all the unpaired valence electrons in order for the atom to be stable and have that full valence electron shell. So if we look at the structure on the right hand side here, we can see that there's two valence electron shells around the nucleus. So in the nucleus we've got our protons and neutrons shown as red and blue circles here. And then our first electron shell in black has two electrons in green here, so that shell is full. And then the next electron shell, which can hold up to 8 electrons, actually only has 6 in it. So we've got a pair of electrons here, another pair up top, so that gives us 4 electrons, and then 2 single electrons or unpaired electrons. So what would have to happen to this atom for it to become stable? Well, these unpaired electrons need to be paired. And how could they possibly become a part of a pair? That's where we need to do the bonding. And for the organic compounds, that's going to be the covalent bonding. So our atom would have to find another atom to be able to covalent bond and fill this valence electron shell here. So as it says in the description here, it's shell 2 that's the valence electron shell here because it's the one that's furthest away from the nucleus. So if there was another atom that came in, for example, a nitrogen that had some valence electrons that were unpaired, as I'm representing here as a dot, we could actually have some sharing between our atom here and nitrogen, and that would actually allow it would allow the valence electron shell of the atom to be filled. So that's the basis of how compounds are formed. We've got atoms coming together, sharing their unpaired valence electrons to get full valence electron shells. So a little bit more detail now about how this actually works. So we've got our valence electrons, and as we saw in that previous representation, we saw that they could be paired, and if the electrons are paired, essentially they're not going to be part of covalent bonding. This is because they're already stable and therefore unreactive. So we can say that they don't contribute to chemical bonding. The valence electrons that we're more interested in are actually the unpaired electrons. And that's because these ones are unstable and therefore reactive. And these are the ones that need to be paired in order to have the atom have a full valence electron shell. And that means that these ones are the ones that do contribute to chemical bonding. So when we're looking at how an atom is going to bond, what you really need to consider is how many unpaired valence electrons there are. So we can work this out from looking at what group an atom is in the periodic table, but there are some common ones that it probably is just worth memorizing, which we'll see in a later slide. So as we can see here from the slide, we've got carbon and oxygen with specific numbers of valence electrons. So carbon has 4 and oxygen has 6. So how could we work out how many valence electrons these two atoms have? Well, you can actually look at the periodic table and work out which group they're in. So for group A elements, which are the representative elements, the number of valence electrons that the atom has is equal to the group number. So for carbon, it's in group 4, as shown by the Roman numerals here, therefore it contains 4 valence electrons. And for oxygen, it's in group 6 and therefore contains 6 valence electrons. So you can see how the number of the group is actually matching the valence electrons. However, this is telling us the number of valence electrons. It's not telling us the number of unpaired valence electrons, which is what we really need to know to work out how it's actually going to bond.